Okay, so here's the solution for number 7. It asks us to use node voltage method to write a complete set of independent equations and then to solve for the unknowns Ix and Vx. Now, it tells us that we can simplify the circuit. So if we were to take that approach, there's a couple things we can do. We can first get rid of this branch entirely because it's being shorted out by this middle branch. And using the same logic, we can also get rid of this dependent current source because it is also being shorted out by this path. So if we were to do that, we can redraw the circuit and it would look something like this. Now, with that being said, right, I know a lot of people don't like to simplify and redraw circuits in case they redraw something wrong and then get the entire question incorrect. So with that in mind, I'm going to go ahead and just solve the circuit as it appears because I'm assuming that most people would take that approach. So for using node voltage method, the first step is to identify all extraordinary nodes. So here we have this big yellow node, we have this brown node, and this red node right above it. So that's 3 extraordinary nodes that we have identified. And now from here, we can choose one of these nodes to be our reference node. And now we're going to want to pick the biggest node to be our ground because that's going to make our lives easier. And that's what we want to do. We do not want our lives to be difficult because Circuits 2 is already difficult enough. So we're going to pick this yellow node to be our ground. And then we just define some terms for our other 2 nodes. Now, I want you to look very closely at this brown node right here because we have a voltage source that is in between it and the other side is connected to our ground. So we have a supernode here, specifically a quasi-supernode, which means that one of the battery's terminals is connected to our ground, which means that we can just call this brown node 6 volts. We can just simply say this node is 6 volts. Now, if this battery was reversed polarity, then it would be a negative 6 volts, but it's not, so it's positive. Now for this red node, we are going to have to create a variable for it because there is no supernode attached to it. We do have these batteries right here, but there's a resistor in between it. So that's not a supernode, so we have to define something, call it V1 at this node. And then from there, we just write our node voltage equation for V1. So that's going to be this, V1 plus 0.3 Vx over 1 ohm minus 3 amps plus V1 minus 6 volts over 3 ohms, and then plus V1 minus 5 volts plus 3 volts over 10 ohms. That is equal to 0. And that's our only unknown node voltage variable. So that's the only equation that we're going to need for node voltage at least. But what we do have to do now is identify any dependent variables in our equation. And here we have one, we have Vx. So in order to solve for this equation, we need a second equation involving Vx. Now, there's a couple ways that we can build an equation like this. One way is to do a KVL. And there's multiple paths that we can take. We can go this way. We can go this way. But what if I told you we can go this way? We can just jump straight from here back to where we started. The reason we can do that comes down to the definition of node voltage variables. So I don't know if they went over this too much in Circuits 1, but when you're defining a node voltage variable, what you're saying is that variable is with respect to your ground. So for instance, if V1 was 3 volts, what that really means is that this red node is 3 volts higher than our yellow node. And that's why we can call this brown node 6 volts, because we have a 6 volt battery that is in between this node and our yellow node, our ground node. and we know that it's a 6-volt difference. So we know that this 6 volts is with respect to our ground. And it works the same way for node voltage variables. Even though it's not directly connected to the ground, there's still a voltage difference of V1 across the two. So if we were to do a KVL, we could just jump this gap and write that voltage as plus V1. And so what that equation would look like is this: 0.3 Vx minus Vx, because we're going across the 1 ohm resistor, and then plus V1 is equal to 0. Now, if that didn't make sense, here's like another example on a completely different problem, right? Let's say we were to call this node Vx, and we call this node our ground, which obviously goes all the way down there. And let's say we just do a hypothetical KVL of something like this, where we start right here and we go up through here, and rather than going something like this or something like this, where we go through all these different components, we can actually just go straight to ground and then just go across this resistor and be done. Because this Vx is with respect to this yellow node. So you can jump across this voltage, or jump across this gap, and represent it as just plus Vx. And so that was just another example to really try to hammer that concept down. If that still doesn't make sense, maybe I can do like a separate video on KVLs entirely, because that is definitely a super important concept to understand and to know for circuits too, because it will come up on quizzes, exams, and whatnot. So yeah. And one more way to help you kind of see that, another way of sort of thinking about it, is like this, right? We know that this yellow node is at 0 volts, right? Because it's our ground. And this battery tells us that this node right here is at negative 0.3 Vx, because we're going down 0.3 Vx from 0. So we can call this blue node negative 0.3 Vx. And this voltage difference tells us that this red node is 1 Vx higher than this blue node. So we can call this red node negative 0.3 Vx plus Vx, because we're going up Vx from here to here. In other words, it is just 0.7 Vx, which if we were to solve this equation for V1, you would get the same thing. So again, that's just another way of thinking about it. Both, ways of thinking gets you the same answer. It's just whatever you feel most comfortable with. So with that all in mind, you can plug these two equations into your calculator and solve for V1 and Vx. However, the question asks us to solve for all unknowns, so we also need Ix. But as we know, this current is the same as this term right here. So we can just take that and say that Ix is equal to V1, and I'll just combine the voltages to get minus 2 volts over 10 ohms. Oops, V1 is not equal Vx. V1 equals something, and Vx equals something, and Ix equals something. So if you were to plug all these equations in, you should get your answers of 3.99 volts and 79 milliamps. And I will plug these into the calculator to verify that those are the answers that you get. And as long as they match, then I will send this video.